Okay, so today we're going deep on quantum teleportation.
Uh-huh.
And I know what you're thinking.
Beam me up, Scotty.
Exactly. But hold your horses for a second.
Okay.
Because we're not talking about teleporting people Star Trek style.
Right.
This is about transferring quantum information.
Yeah.
You know, the really fragile stuff that makes quantum computers so powerful.
Absolutely.
But there's a catch. It's really, really hard to do.
It is, yeah.
Like you need this perfect entanglement between particles.
Mm-hmm.
Then you have to measure things super precisely.
Right.
And then somehow send those measurement results somewhere else.
Mm-hmm.
And then the receiver has to take all that and actually reconstruct the original quantum information.
Yeah. A whole process.
Yeah, and getting all of that to work consistently is a huge challenge.
It is. The quantum realm is just inherently noisy.
Yeah.
And these quantum states, they're unbelievably delicate. We're constantly battling this thing called decoherence, which is basically when quantum information interacts with its environment and kind of leaks out.
Right, it loses its quantumness.
Exactly, and just maintaining that connection long enough to do teleportation, that's a feat in itself.
Yeah, so imagine this, we're trying to get this super secret, super fragile piece of quantum data from point A to point B.
Okay.
But without actually moving the physical particle itself.
Right, like a fax, but for quantum stuff.
Kind of, but way weirder. And now here's where things get really interesting.
Okay, and I'm intrigued.
We're going to see how propulsion science might actually have some of the answers we've been looking for quantum teleportation.
Propulsion science. It's rockets and spaceships.
Yeah, well, not just rockets, but all sorts of ways to move things through space or manipulate fields. And it turns out that the same kind of thinking that goes into designing those systems could be what we need to make quantum teleportation practical.
That's a pretty unexpected connection.
It is.
Okay.
But when you think about it, both fields are pushing the boundaries of how we understand and manipulate reality at the most basic level.
That's true whether you're warping space-time for a super advanced propulsion drive or trying to keep these entangled particles connected.
Mm-hmm.
It all comes down to controlling the fundamental building blocks of the universe.
Exactly.
Huh.
So today we're going to dive deep into how these principles from propulsion science,
Okay.
and we're talking about everything from the strangeness of quantum mechanics itself to manipulating electromagnetic fields, even quantum tunneling, and some really advanced materials.
Wow, it's a lot to cover.
It is. But how can we use all of that to meet those core requirements of quantum teleportation? Keeping entanglement strong, making super accurate measurements, and transmitting that information reliably.
Sounds like a challenge.
It is, but it's also a huge opportunity. What's really cool is how ideas can jump between these seemingly separate areas.
Yeah, sometimes the best solutions come from looking at a problem from a completely different angle.
Exactly. So let's start with these quantum electromagnetic fields. One of the biggest problems in quantum teleportation is keeping those entangled particles well entangled.
Right, that connection is so fragile.
It is the slightest nudge can break it. And in propulsion science, there's this focus on manipulating fields, right?
Yeah, we're talking about things like Casimir-based propulsion and electromagnetic thrust arrays.
Right, so how can we use what they're learning there to keep these quantum states stable during teleportation?
Well, if you really break it down, both Casimir propulsion and electromagnetic thrust are about shaping electromagnetic fields with incredible precision, but at a tiny scale.
Yeah.
Like in Casimir propulsion, you're basically using these carefully designed surfaces to change how the quantum vacuum fluctuates.
Oh, wow.
And that creates a force, and electromagnetic thrust is all about using those tailored fields to actually move things.
Okay.
So the key takeaway here is controlling those fields.
Right.
And we can apply that same level of control to the quantum world.
So give me a picture of how that would actually work to protect these entangled particles.
Okay, imagine using nanoarrays.
Nanoarrays.
Yeah, basically these incredibly small structures arranged at the nanometer scale.
Okay, tiny.
To create super precise electromagnetic fields right around the entangled particles, and those fields would act like a shield against decoherence.
So like a force field.
Yeah, but for quantum information.
Okay, a tiny force field just for the qubits.
Exactly, it's like creating a little bubble of stability.
Right, making those quantum states less vulnerable to all the noise around them.
Exactly.
That makes sense.
Yeah.
So we're giving those qubits their own little safe space.
Precisely, and there's another cool idea involving these things called Casimir cavities.
Casimir cavities.
Yeah, think of them like tiny boxes that can actually quiet down the quantum jitters around the qubit.
Like noise-canceling headphones, but for quantum information.
You got it. By carefully controlling the quantum vacuum energy inside these cavities, we can create this incredibly calm environment that lets the quantum information survive for much longer.
And haven't we seen some promising simulations about this?
We have. There was this prototype simulation that showed a nano-engineered Casimir cavity with 95% isolation could increase a qubit's coherence time from a typical 50 microseconds, which is incredibly short, to around 1,000 microseconds.
No, so 20 times longer.
Yeah, it's a massive jump in stability.
That's amazing. So we're talking about putting these qubits in these special Casimir boxes to protect them.
Right.
And then using those field manipulation arrays to carefully guide the photons or ions that carry the quantum information.
Exactly. It's about creating a controlled and isolated environment throughout the whole teleportation process.
Okay, so next up, quantum tunneling. This always sounds like something out of science fiction to me.
It does have a certain ring to it, doesn't it?
It does. Particles just passing through barriers, like they're not even there.
Right, like ghosts.
Yeah, but this is a real thing that physicists are looking at for propulsion.
Yeah, things like quantum tunneling drives.
Right. So how does that connect to quantum teleportation?
Well, it's about improving the speed and reliability of sending the measurement results from the sender to the receiver.
Okay, so remind me how that part works again.
All right, so after the sender does their measurements on the entangled particle and the one carrying the unknown quantum state, they have to send the results of those measurements to the receiver.
Okay.
But they have to use a regular classical communication channel.
Like the internet.
Exactly, and that can actually be a bottleneck. It slows down the whole process.
So we're doing all this super fast quantum stuff.
Right.
But then we're stuck waiting for good old-fashioned bits to catch up.
It's like having a supercar stuck in traffic.
Yeah, quantum traffic jam.
And that's where quantum tunneling might help.
Okay, how?
The idea is to use tunneling to speed up that classical data transfer.
So instead of electrons having to go through a wire, they just tunnel through a barrier.
Yeah, basically we can engineer these things called tunneling junctions, which are basically super thin barriers between conducting materials.
Uh-huh.
And by tweaking the properties of those junctions, we can make electrons tunnel through much faster. And our simulation suggests that this could boost the efficiency of that classical channel from about 70% to almost 90%.
It's a pretty big speed boost.
It is. And it's often overlooked because everyone's so focused on the quantum side of things.
Right. But even the classical parts can be improved with quantum principles.
Exactly.
Now, aside from speeding up the data, could tunneling be used to guide the particles themselves?
The same principles could be applied to actually guiding the photons or electrons that carry the quantum state.
How would that work?
By designing potential barriers, we can kind of steer those particles through obstacles using tunneling.
So it's like they have their own little quantum tunnels.
Yeah, it's a very subtle way to control their movement.
Very cool. Okay, let's shift gears a bit and talk about materials. Science. Superconducting materials and magnetic fields are really important in propulsion technology.
They are.
But how can we use them to make quantum teleportation more reliable?
Well, superconductors have this amazing property where they have zero resistance to electricity below a certain temperature.
Right.
And that's perfect for creating these super stable, low-energy environments.
Okay.
So if we use superconductors like niobium in the hardware that holds our qubits, it can massively reduce electrical noise.
So it's like a noise-canceling system for the qubits.
Exactly. It's like putting them in a perfectly quiet room.
I like that analogy. And what about manipulating magnetic fields?
Well, we can take inspiration from propulsion systems that use magnetic levitation or confinement.
Right.
And use magnetic fields to create these tiny traps that hold and stabilize the quantum states.
So like little invisible containers.
Yeah, and that helps prevent them from interacting with their surroundings and losing their coherence.
Okay, so again, it's about controlling the environment.
Right, keeping things as calm and stable as possible for those delicate qubits.
Now let's zoom in even further down to the nanoscale gaze. Nanotechnology is essential for all sorts of futuristic propulsion concepts.
Absolutely.
But how can these tiny tools help us in the equally tiny world of qubits?
Well, at the nanoscale, we can achieve an incredible level of control. Okay.
We can use nanoarrays and nanostructures, the kind being developed for propulsion systems, to manipulate individual qubits or even entangled pairs with unbelievable precision.
Wow.
And we can also use them to significantly improve the way we capture photons or ions, which is critical for those high-precision quantum measurements.
So give me some concrete examples of how we would actually use those nanoscale tools.
All right, imagine using nano-engineered metamaterials as these super efficient photon capture arrays.
Metamaterials?
Yeah, they're materials that have properties we don't find in nature because we structure them at the nanoscale.
Okay.
And these arrays could be designed to absorb and process entangled photons really effectively.
So we're capturing as much quantum information as possible.
Exactly. It's like a perfect quantum net that catches every single photon.
I like that. And what else?
We can also use nanostructures to build these nanoscale optical circuits.
Okay.
And those circuits would guide the photons or ions involved in Bell state measurements.
Right. The measurement that tells us about the entanglement. Exactly. And this would allow us to make those measurements with really high accuracy.
So basically we're creating these incredibly precise tools for manipulating light and matter at the quantum level.
Precisely.
That's amazing. So it seems like we're talking about some really incredible possibilities for short-range teleportation.
Yeah, within a lab or a quantum computer.
Right, but what about long-distance teleportation?
That's the really big challenge.
It is. How can propulsion science help us with that?
Well, the main issue with long-distance teleportation is maintaining the quantum communication channel over those distances.
Right. Those entangled particles, especially photons, can get lost or lose their entanglement as they travel.
Exactly, and that's where those field manipulation techniques we talked about come in.
So we're shaping those electromagnetic fields to guide those particles over longer distances.
Exactly. We can adapt the same principles used in electromagnetic thrust for propulsion to create these highly directional channels that protect the entangled photons as they travel.
So it's like a protected beam of light.
Yeah, a quantum highway, if you will.
I like that. And on top of that, could we use electromagnetic arrays to amplify the signal?
We could, as quantum signals weaken over distance,
right.
We could use those arrays to boost the signal strength without adding too much noise.
Because extending the reach of our quantum communication.
Exactly.
Okay, so we've talked about a lot of different techniques here, all borrowed from propulsion science, each one tackling a specific problem in quantum teleportation.
Yeah, the whole toolkit.
And, of course, we can't talk about advanced technology without talking about AI.
Of course.
So how does AI fit into all of this?
Well, AI is all about optimization.
Right.
And we can use those same algorithms that are being used to design and control complex propulsion systems to improve quantum teleportation as well.
So making the teleportation process itself smarter and more efficient.
Exactly. We can use AI to fine-tune a whole range of parameters.
Like what?
Well, things like the strength and shape of the electromagnetic fields, the properties of the tunneling junctions, even the design of the Casimir cavities and nanostructures.
Wow.
It's about using AI to explore all the possibilities and find the absolute best settings for every single component.
That's really cool. So it's not just about borrowing the hardware and the physics, but also the intelligence behind those systems.
Right.
Now, we've talked a lot about the theory, but has any of this been put into practice?
It has. We've developed a conceptual prototype that combines several of these principles.
A prototype? Tell me more.
It focuses on three main areas. First, using a Casimir cavity to isolate the qubit. Second, using electromagnetic field manipulation for entanglement stability. And third, optimizing the classical communication with quantum tunneling.
And what kind of performance improvements are we seeing in the simulations?
The results are really impressive. The Casimir cavity alone could increase the qubit coherence time from 50 microseconds to around 1,000 microseconds.
Wow, that's huge.
It is, and the electromagnetic field manipulation could boost entanglement fidelity from 85% to 96.5%.
That's a big jump.
It is, and the optimized tunneling could increase classical channel efficiency from 70 to 89%.
Wow, and what about the overall teleportation fidelity?
That could jump from around 70% to 95%.
Those are some serious improvements.
They are. It's not just incremental, it's a potential game changer.
So what's the plan for taking these ideas and actually building these systems?
We're looking at a three-phase approach.
Okay.
Phase one is all about research and modeling.
So really understanding the details.
Exactly. We'll be using tools like Qiskit and Cirq to build detailed simulations.
Okay.
Phase two will be experimental prototyping.
So actually building the components?
Right. We'll be developing those nanoarrays and Casimir cavities and testing those electromagnetic field arrays.
In the lab.
Exactly. And then phase three is system validation.
So putting it all together.
Right. We'll be integrating the components with quantum hardware and testing the whole system, including long-distance teleportation.
That's a really exciting roadmap.
It is. It could really change what's possible with quantum teleportation.
So it sounds like propulsion science could be the key to unlocking the potential of quantum teleportation.
It could, and it shows the power of looking at problems from different angles.
It really does. Who would have thought that the quest to travel the stars could help us solve one of the biggest challenges in the quantum world?
It's a reminder that there are probably all sorts of unexpected connections between different fields just waiting to be discovered.
Exactly. And who knows what other breakthroughs are out there waiting for us to find those connections.
It's an exciting time to be exploring these frontiers.
It is. Thanks for taking this deep dive with us today.
It was my pleasure.
And to all our listeners out there, keep exploring those unexpected connections. You never know what you might find.
You never do.
Until next time, keep diving deep.
See you then.